Okay, so last time we start to work on radiation from the localized oscillating sources. These sources are the current densities or charge densities. So what we have done, we said that we have some localized charge density or current density is better, and oscillating harmonically in time, and we are interested in to look at the fields, basically electric field and H, magnetic field. So what tools we have? We have vector potential. So knowing the vector potential, we can calculate the H field, and using the Maxwell's equations, Faraday's or Ampere's law, modified Ampere's law, we can estimate the electric field. So we use the Lorentz condition, and we know that the solution of the non-homogeneous wave equations using the Green's function, and the vector potential is in the following form: mu 0 over 4 pi integral of current density over x minus x prime e to the I k x minus x prime d cube x prime. So this is coming from the non-homogeneous wave equations under the Lorentz conditions. So we said that let us look at the problem at 3 zones. What are the 3 zones? So emitted radiation has some wavelength, lambda. We can look at the radiation at far field zone. At this zone, R is much greater than wavelength and greater than the source. And the other zones, our point of interest could be closer to the wavelength or less than the wavelength. So for the far field zone, we we derive the vector potential in terms of in the following form. We make a Taylor expansion to the exponential, and we find that the vector potential in the following form: mu 0 over 4 pi e to the I k r over r summation n 0 to infinity minus I k n over n factorial current density n dot x prime to the n power integrated through the volume. So that was the approximation at the far field zone. Source is small in dimensions relative to the wavelength, and our point of interest is much greater than the wavelength. So the spatial case n equal to 0, the lowest order of this series, could be expressed, indeed I proved to you, in terms of in the following form: a of x is minus I mu 0 omega over 4 pi e to the I k r over r times p. P is the electric dipole moment. X prime times the charge density integrated through the volume, that is the electric dipole moment. And I said that this vector potential is behaving as a spherical wave. So today, this is the point we stopped last time. Today, we will try to calculate the magnetic field, electric field, Poynting vector, and power emitted per unit solid angle if we have an electric dipole radiation. So basically, we are discussing the electric dipole radiation. The simplest one could be the following. So suppose that we have plus Q minus Q charge. They are not static, oscillating in time. Their charges are changing in time as a cosine omega t or sine omega t. And it could be expressed easily in terms of exponential complex numbers. So let us start to calculate the H. So the calculation of H is easy, but the calculation of the electric field is a little bit handy. So this is equal to curl of E over mu 0. And what is our vector potential? A. So if you plug the A over there, we are going to obtain the following: minus I mu 0 omega over 4 pi curl of e to the ikr over r times the electric dipole moment. So electric dipole moment actually is a constant vector when you integrate it through the whole space of the charge densities. So this is nothing but the curl of a scalar function times the vector, and that is equal to minus I mu 0 omega over 4 pi gradient of the scalar function, gradient of e to the ikr over r, cross product electric dipole moment plus e to the ikr over r scalar function, curl of p. P is a constant, therefore this term will be 0. So if you calculate the gradient of e to the kr over r, so what we are going to obtain? So I forget to write the mu 0, so that will be cancelled. So the H will be minus I omega over 4 pi. So this is a gradient in spherical coordinates, but r is depending on the r, it's a radial coordinate. So we can define that the gradient with respect to the r only del over del r hat, and I'll take later r hat as the n hat unit vector. Okay, so because this doesn't have any other this doesn't depend on any other coordinates like at theta and phi. So all you have to do, take the just partial derivative, take the gradient with respect to the r using the partial derivative of r del over del r. So if you do this, you will obtain the following. So the first term, derivative of the exponential, is ik over r, and e to the ikr. Derivative of the 1 over r will be minus 1 over r square. That will be totally e to the kr over r square. R hat is the direction of the gradient, and instead of r hat, I'll write n hat, n hat represents the unit vector along the radial direction, cross product electric dipole moment. So if you arrange the terms, you are going to obtain the following. So take the Ik over R outside the parentheses, so you will obtain minus I omega over 4 pi Ik times, take the parentheses of e to the ikr over r, and the rest will be 1 minus 1 over ikr n cross p. So you can handle the things very easily. Omega is equal to k times c, and k times c, so this is k square, c, I and I is minus, and altogether H field, auxiliary field, will be the c times k square over 4 pi e to the ikr over r, that is the spherical wave term, 1 minus 1 over ikr n cross p. So basically H field goes with 1 over r times 1 over r square terms. At the far field, this 1 over r square term will goes to 0 much faster, and it has the form of spherical wave e to the kr over r. That means that as as the distance goes on, the amplitude of the H decreases as a 1 over r. So this spherical wave is very important. We will see when we calculate the Poynting vector altogether, they will be independent of r. That means that we can see that the radiation from very large distances. We can see that the radiation from the cosmic background, from the early universe and so on, because the waves are spherical waves. So I'll point at that point later on. Okay, this is the H field. So this calculation of the H is easy. So the difficult part is the calculation of the electric fields. So I will carry the calculation at some point, and I will write the result, and I will discuss the result. So E electric field could be written as I Z0 over K curl of H. So you can obtain this using the modified Ampere's law. You have curl of H, which is equal to current density. Our point of interest, there is no current density, so put 0. And you have what? Plus partial derivative of the del electric displacement over del T. Instead of del over del T, you can substitute minus I omega, and then you can solve that the electric field in that form. So let us try to calculate the electric field. I times Z0 is the impedance of the free space, that is mu 0 over epsilon 0 times 1 over k is here. The first term is the impedance of the free space, and what else? I have to calculate the curl of H, and H is here. And so let me take the coefficients outside. So the coefficients are what? C k square over 4 pi, this is the coefficient, and curl of this bunch of terms, including the spherical waves, and that is e to the ikr over r 1 over ikr n cross p, n is our unit vector. So let us play quickly with the coefficients. K's will be cancelled, and C is 1 over square root of mu 0 epsilon 0. Mu 0 terms will be cancelled, and what we obtain, what is left, I times k times square root of 1 over epsilon 0 times 1 over epsilon 0 makes 1 over epsilon 0. The units will be ik over 4 pi epsilon 0. So we pick up the 4 pi epsilon term in standard units. So the rest is curl of, let me take the n cross p ahead, n cross p times e to the ikr over r 1 minus 1 over ikr. So this calculation will be a little bit long, but I have to do it at some point because you have to see that some steps. So again, this is the curl of a vector times the scalar, and that is equal to ik over 4 pi epsilon 0, gradient of the scalar term, this stuff is the scalar, gradient of e to the ikr over r minus e to the ikr over ikr square. So I distribute the 1 over r inside. Cross product n cross p plus the scalar term e to the ikr over r minus e to the ikr over ikr square, curl of n cross p. So this is the electric field. So this will be the long expression, long calculation, but we will see a nice result at the end. So I want to continue the calculations. So did I do correctly? Gradient of the scalar is here, cross product n cross p, and I have scalar in here, curl of n cross p. So I'll start to play with this term, this term. So h should be stay here. Let us start to play with the calculation of the curl of n cross p. So curl of a cross p is an identity. You can use the indices to derive, or you can use the first page of your book, so or any mathematical books. So the curl of n cross p is equal to n divergence of p minus p del dot n. N is a unit vector along the r head, plus p dot gradient along n head, and n head gradient p. There are some terms 0. Which terms are 0? Whatever the derivative is the electric dipole moment, that is 0, because the electric dipole moment is a constant vector. So basically this term is 0, and this term x to the p, that will be the 0. Now we will start to play let me call 1 prime, let me call this as a 2 prime, and let me try to evaluate what is 1 prime and what is 2 prime. 1 prime is what? P dot P not a P divergence of n. So let me keep in that form. So let me calculate the divergence n. It's better. Then I can multiply P. So divergence of n is divergence of x in 3 dimension over x magnitude. So x over x magnitude, this is the n unit vector. So this is a vector times the scalar, and that is equal to gradient of 1 over x magnitude. That is a vector, gradient of the vector is vector, and we are getting a scalar at the end. So therefore take the dot product with x, gradient of the scalar dot product with x, plus divergence of x with x magnitude. So tell me, what is the gradient of 1 over x? Do you remember? Gradient of 1 over x. So from the first part of the course, that is nothing but x over x cubed, and you have dot x. And what is the divergence of x? You can say this very easily. X, what is x? X hat plus y hat plus z. If you take the derivative with respect to the x, you will have 3. That will be 3. 3 over x. That will be the 3 over x. And what you are going to obtain, this is x squared, this is 1 over x. X magnitude is at the same time is what? R. Okay? X magnitude is r, so this is minus 1 over r cubed, minus 1 over r, sorry, this is plus 3 over r, and all together that is nothing but 2 over r. So this is the contribution of the first term, so then this is nothing but 2 over r along electric dipole moment. And let us work on, so let me erase this, I can rewrite it later. Let me work on the second term. So it is, the second term is a little bit more longer. So we have, let me say 2 prime p dot gradient along n. So let us write this component by component. Px del over del x n hat, py del over del y, py del over del y n hat, pz del over del z n hat. So n is again a unit vector, x over x hat. So that is equal to px del over del x over x magnitude, and similarly py del over del y x over x magnitude, and the same thing, let me do one more, pz del over del z, z over x over x hat. X vector is x I y j z k. X magnitude is square root of 2 x square plus y square plus z square. If you take the derivative, what you are going to obtain? If you take the derivative of the upper term, you will have I times the rest. If you take the derivative of the lower term, you will have 2x times minus 1 over 2, and the power will be, not the power of the whole stuff, will be 3 over 2. So let me do one term and conclude the result quickly. That is px times derivative of the x is I divided by x square plus y square plus z square. Derivative of the second term is minus 1 over 2 times 2x times the x, xi yj zk, divided by x square plus y square plus z square 3 over 2, and close the parenthesis. So do you have any question here? Okay, I take the derivative with respect to the x, then divide this, then I take the derivative of this. I have 2x 1 over 2 minus, because this is in down, and times the x is xi, yj and zk. If you do this for the other terms, you will have the similar terms. And then what will be the full result? So we are trying to calculate the p dot gradient n, p dot gradient along n. And what we can find? What is this? This is px over r. You will have here what? Py. What will be this? What will be this term on the bracket? If you take the derivative with respect to the second one, that will be j over r, and this one will be k over r. So if you do this, this will be j over same thing, and that will be k hat over same thing. So altogether pxi, pyj, pzk is equal to p divided by r. So did you see this? You all see? Yeah, this is trivial. So if you put instead of x, take the derivative with respect to y, you will have j. Take the derivative with respect to the z, you will have k hat. And if you look at the second term here, 2's will be cancelled. This is nothing but x vector or r vector. This is nothing but x cubed. The tricky thing here, what is this? Px times x along r. Okay, the first term. Px times x along r. If you do the same thing here, what you are going to obtain? Py times y along r. That will be the pz times z along r. So divided by, all of them divided by r cubed. So the second term will give you p dot r or p dot x in 3 dimension along r over x cubed over r cubed. So if you do the, for example, the third term, you will get what you are going to get minus 2z over z and r over r cubed, for example. And if you do the, for that one, you will obtain 2 over 2 y r over r cubed. So as a summary, we have this term here. So if you look at this as a whole, we will get the following. What we are trying to calculate, we are trying to calculate curl of n cross p, curl of n cross p, we want to calculate. And we reduce this calculation to 2 terms, that is minus p divergence of n plus p dot gradient along n. And for the first term I calculated 2 over r for the 1 prime, and for the 2 prime I calculated that. So if you put the things together, you will get the following. So 2 over r is the divergence n, and that is along minus p. So that makes minus 2p over r instead of this term. So basically this is nothing but 2 over r, and p is the minus p over r. And other term, p dot gradient along n is p over r minus p dot r over r cubed. So this is nothing but minus p over r. So we have terms going on with the 1 over r square, and 1 over r cubed. So this is the calculation of the curl of n cross p. So I'll show you quickly what is the other term, and I come to the point as possible, as quick I can do. So basically this curl of n cross p, where is this, minus p over r and minus p dot n over r over n hat. So let me tell you one thing here. R is nothing but r magnitude n hat, r magnitude n hat. So these r's cancel and this drops to the 1 over r, and that is n. But we have the terms is related 1 over r and r square, and that makes the terms 1 over r square, 1 over r cubed. So I will interpret those things when we come to the latest point, not now. So the next thing is the gradient of this term. So let me try to calculate the gradient from here. So the derivative, so I'll just write the derivatives. The first upper term, IKR over R. The second derivative with respect to the second one will be minus 1 over R square e to the IKR over R square, that will be the second term, minus the above term, this one, the exponential brings IK down, IK times e to the IKR over IKR square, and the below term will make what? Minus 2 makes plus 2 e to the IKR over IKR cube, and the rest is cross n cross p. So IK and IK cancel, and these are the 2, and that is nothing but 2 minus 2 of the same thing, e to the IKR over R squared. So, and if you take the gradient, you will get this along R hat. Okay, so if you take that, you should obtain a vector, and that is n R hat. So basically, this is n cross p, n cross p. If you look at the all bunch here, only one term is the spherical wave. This is this, that is alone, e to the IKR over R. This goes 1 over R square, this goes 1 over R cube, this goes as 1 over R square because we have 1 over R, this goes as 1 over R cube. So I will separate the spherical wave term and combine the other terms. So basically, now I am coming to the end quickly. I am keeping the spherical wave term. I have IK, and IK here makes minus k square. IK times IK minus make k square. In order to get rid of the minus, I will switch the cross product. I will take the n cross pn. So, in the parentheses of 1 over 4 pi epsilon 0, I have k square n cross pn times the spherical wave, k square n cross p cross n e to the IKR over R. This is only the first term. I am studying only first term. Where is the first term? IK minus k square n cross p. I switched the order, I wrote that. Okay. So this is the spherical wave term for the electric field. And the rest is the exercise for you, but what you are going to need, let me bring this to the down. We have n here, n cross p. If you write the openly this, what is this? Write the openly this. This is n dot p along n minus n dot n along p. Okay? I pick the first term and put it there. For the rest, you have what? For the rest, this term, n cross p. So for the rest term, you do it by yourself as an exercise. Open this as a n cross p along n minus n dot n minus p. Okay, n dot n is 1. Oh. If you look at this, you have what? You have what? P. You have p. You have what? N dot p and you have n dot p n. You can combine everything, okay? So if you do this carefully, you will get the following. So I don't want to do this on the blackboard, because you can do this by a pen and paper by yourself much more easily than what I am going to do in the blackboard if I try it. So the result will be the following. 3 n hat n dot p minus p 1 over r cube minus ik over r square e to the ikr. Yes. So if you take the coefficients of n dot pn, you will get this bunch. If you take the coefficient of p, you will obtain that. So you can verify this by yourself easily. So what does this long formula tell us? So let us rewrite the H again. So we have E and H for an electric dipole radiation. So H is C k square over 4 pi e to the ikr over r 1 minus 1 over ikr n cross p. So after a long derivation, we find something. And what are those? So what are those things? What you see here, if you go to the far distances, only dominated terms are what? 1 over r. 1 over r square and 1 over r cube die much more faster. And here, if you go to the far distances, again 1 over r is important. So let us go to the far field and look at the H and E at the far field. So when Kr is much greater than 1, or 2 over wavelength over r time r over wavelength is much greater than 1, that is the far field zone. So H goes to H field takes the form of what? C k square over 4 pi e to the ikr over r n cross p. And electric field takes the form of what? So if you take the far field, 1 over r square and 1 over r cube terms are dropped to 0, and you will obtain only this term, 1 over 4 pi epsilon 0 k square n cross p cross n e to the ikr over r. Now, at the far field, this is the structure at the far field. Only 1 over r terms is surviving. So can you make a connection between the E and H? So if you look at carefully, you have in the H n cross P, in the E you have one more cross product. So you can plug these things together. So if you do, you will obtain the following. So let me do for you. This is the important point. So the electric field, take the 1 over epsilon 0 out, multiply by C divide by C, and you will get C k square over 4 pi n cross P e to the ikr over r cross n. So these are the same. What I do, I take the epsilon 0, multiply by C, divide by C, put the 4 pi inside. And what is this whole bunch? What is this whole bunch? What is C k square over 4 pi n cross P ik over r? What is this? H. What is the C? That is 1 over square root of mu 0 epsilon 0. One of the terms takes into the square root of 2, and you will obtain this is equal to, that is equal to square root of mu 0 epsilon 0 h cross n. Is this something we see in the past? Yes. Yes, this is the behavior of the plane waves. These are not plane waves, these are spherical waves. Amplitudes of the waves are decreasing as a 1 over r, but if you go to the far field zone, that tells you that E, H, and N are mutually orthogonal to each other. And that is the impedance of the free space. That's 0. So for the radiating zone, radiating fields, all the times you can use this H cross N. Okay, if you go to the far field zone from the source, the N, E, and H are mutually orthogonal to each other. But in general, if we are somewhere, N cross P is what? N is the electric dipole moment, N is the point of interest. In general, what is N cross P? Is a transverse to the R hat. So if you say this is the N hat, N cross P, this term is what? Outside the blackboard. So basically, if you look at any point, that you will find that the N hat and H are orthogonal to each other, R hat and H. But for electric field, there is not such condition. So there's the electric field could be along to P. That could be orthogonal and that could be N. So if in general is something like this, electric field it has a parallel and perpendicular components to the N. But if you go to the far field zone, if you go away from the source, electric field also perpendicular to N and H. Okay? In the close to the source, electric field is more, many components has. But even in the far field, zone, they mutually orthogonal to each other. So from now on, if we, for the far field zone, we will get this. We will say that the N, H, and E mutually orthogonal to each other. And the amplitude of the wave is decreasing as 1 over r. If you take the amplitude of the wave, this is decreasing as a 1 over r. If you go far distances, E field decreases as a 1 over r. H field decreases as a, again 1 over r. But if you go to the infinity, you can still get a radiation. That is interesting. So I'll come to that point when we look at the Poynting vector, not now. Now, before giving a break, let us look at the near zone. Let us go to the source, nearby the source. Which term is important when you go to the investigate the fields near to the zone, near to the source, sorry. So if you go to the close to the source, near zone, Kr in that case small. So 2 pi over lambda over r is small number. And if you look at the terms, what kind of structure you have, which term is dominated? When Kr is small, first of all, the exponentials are unity. Kr goes to 0. And which term is important? R cube. For that one? R square. Is which term is dominated? R cube or over R? In far field zone, E and H both goes as 1 over R. But in the near zone, only 1 over R cube is dominated. So if you compare the E and H in the near zone, which term is more dominated? electric field because it goes as a 1 over r cube. And if you look at if you write the electric field in the near zone, you will obtain what? 1 over 4 pi epsilon 0 3 n hat dot p over p r cube. Is this field oscillating? Yes, it is oscillating if you multiply with the I omega t, but in space is it oscillating? Is there any oscillatory term here? But here you have e to the kr. With the distance, there is oscillatory term. But for that, no, because when kr is small, this turns to 0. Kr goes to 0, e to the exponential goes to the 1. So in space, there is no oscillator. That's why they call a near static. And another important, what kind of formula is this? Do you remember what is this? This is, what is this? This is a very fundamental formula for the electric field. If you have an electric dipole, static electric dipole, the field lines exactly is this. If you go to the 4th chapter, look at the electric field of the electric dipole, identical in this one. So basically, in near static zone, so this is, let us give a name, near static zone, field lines identical with this one, and that is this. So these are the electric field lines. They are static. So that is the reason they are called near static zone. So h goes as a 1 over r, it's not important. 1 over r square is not important. So h is much is a magnitude, h is much less than e because h goes as what? In the near zone as a 1 over r square, but this goes as a 1 over r cube. So basically, if you go and look at your book in chapter 4, so multiples electrostatic of macroscopic media, dielectrics, where is this? Equation 4.13 is the same as this. So basically, it is called near static zone because when you go to the closer to the source, the electric field is dominated. Even the dipole is oscillating. Even if you have electric dipole radiation, so you have only electric field lines. But if you go to the far distances, then you have n hat, and you have what? H cross n. So H cross n. H is in transverse, n cross H is something like this. And the amplitudes are decreasing as a 1 over r, and E is outside or inside. E. Okay. E and H as a magnitude goes as 1 over r in the far field zone, but when you come to the source closer, E is dominated, and the fields are exactly of the static electric dipole. So what is the next? The next thing is important. What is the emitted power per solid angle from the dipole radiation? What is the Poynting vector? I could say before the break one thing for the Poynting vector. Poynting vector goes as what? E cross H. E cross H has 1 over r square. This is the Poynting vector. But if you look at the Poynting vector goes to 0 at infinity. But if you look at that, the integrate through the any cross-sectional area, what is the solid angle of this any cross-sectional area in spherical coordinates? It goes with the what? R square. So r square times 1 over r square cancel. Therefore, you can get the radiation at the infinity. Why? The waves are spherical. If the waves are not spherical, if it goes 1 over r square or something, we cannot get information from the large distances. But now we can get the information. For example, you know that the first light was occurred, what? 14 billion years ago. We can see that radiation because they are 1 over r square, 1 over r. So the waves can be detected at infinite distances. Okay, so this is a very important consequence. So I'll discuss this in the next hour. So I will calculate that the power emitted per solid angle, and then I'll start to study that the magnetic dipole radiation and electric quadrupole radiation.